Alright, Assalamu alaikum. So in this video, we'll be starting off with a new chapter, and that's called Binomial Theorem. Now, this chapter is a part of a O-level Add Math and a S-level Math. There's also a chapter by the name of Binomial Theorem in A2 level mathematics, but it's different from what I'm covering in this video. So if any A2 students are watching this video, watch it just for review because it won't cater to your needs. Uh, if I get time, I will make a video on the A2 level part of binomial theorem as well, but not in this set of videos. So this is a small chapter and it's not a very difficult chapter. So I'll be making, I guess it'll be done in a maximum of 3 videos, and I'll try to keep the videos short this time. Uh, it's a small chapter, but we'll be dedicating 2 complete videos, inshallah, to solving questions on binomial theorem because this is where the real catch of the chapter comes in. So, what will we be doing in these videos? So the first thing that we'll do is that we'll understand what a binomial actually is. And in this chapter, we'll be dealing with what happens when we apply certain whole number powers to binomials. So in this chapter, we'll be discussing what happens when whole number powers are applied to binomials. This is the question that we'll be answering in this chapter. And what are whole numbers? Whole numbers are 0, 1, 2, 3, and so on. Then we'll discuss something called the Pascals triangle. We'll discuss something called the factorial notation. We'll discuss a formula called NCR, and we'll discuss how to arrange powers in a binomial expansion. So now the first thing, what exactly is a binomial? Well, the word bi refers to 2 and nomial refers to terms. So any mathematical expression that contains 2 terms is referred to as a binomial. So because this binomial theorem is a part of algebra, and actually all math is algebra. 2 plus 3 is also algebra. Why? Because you actually do have variables there, but the powers of those variables is 0. But still it is algebra. So a binomial basically is an algebraic expression. It is an algebraic expression containing only 2 terms. So for example, something like A add B. This is a binomial. And I can have anything in place of A and in place of B. So we can have 3x plus 2x to the power of maybe 4. This is also a binomial. Why? Because this is one term and this is the other term. So now let's come to the question that we want to answer in this chapter. That is, what happens when whole number powers are applied to binomials? For that, I want to go back to O-level mathematics, where we studied some identities, and that's where we'll actually begin with. So let's have a binomial, a plus b. We'll use this binomial throughout this video. So what happens when I give a power of 0 to a plus b? Now obviously a would be having a particular value, b would be having a particular value. When I add both of these numbers together, I would get another number which would be having a particular value. Now, we know this from the chapter of indices that you have studied in both O-level math as well and in add math as well, that if anything is given a power of 0, the answer comes out to be 1. So if a plus b is given a power of 0, the whole thing is given a power of 0, the answer that we'll obtain is 1. Excuse me. Now, what happens if a plus b is given a power of 1? And we know this again from O-level mathematics that anything when given a power of 1 remains unchanged. So what we'll get is a add b as it is. Now let's increase the power one more time. A plus b whole squared. Now this time we will be getting three terms, and we know the identity. We have studied that in O levels, and it is a squared add 2ab add b squared. Alright, I'll just bring it a bit in the center because we'll be trying to make a triangle here out of all this. So the more beautifully it's arranged, the better. Plus b squared. Now let's move on with another power. A plus b whole cubed. So a plus b whole cubed is actually a plus b times a plus b whole squared, which is a plus b times a square plus 2ab plus b squared. You can do the working and you will obtain a cubed plus 3a square b plus 3ab square plus b cubed. So I'll write this down here. A cubed add 3a square b add 3ab square add b cubed. Okay, this. Now let's move to a plus b to the power of 4. You can apply the same procedure here, replacing this part with a plus b whole cubed and replacing this term with this one, and you will be obtaining a to the power of 4 add 4a to the power of 3 times b add 6a squared b squared add 4ab cubed add b to the power of 4. One last, a to the power of, a plus b to the power of 5. So a plus b to the power of 5. And this is going to give us a to the power of 5 plus 5a to the power of 4b add 10a cubed b squared add 10a squared b cubed add 5ab to the power of 4 add b to the power of 5. Now I'll just remove this. So now we have a series of expansions here with us. Now what I'll do is I'll make another triangle, and in that triangle I'll just list down the coefficients that we obtained in these expansions. So when we had a plus b to the power of 0, we obtained a simple 1. Then, when I had a plus b to the power of 1, I obtained two terms, each of which had the coefficient of 1. So I'll put two ones here. Then when we had a plus b squared, we had 1, 2 is the coefficient of this entire thing, 1. So we have 1, 2, 1. Here we go. For the third time, in the third term of the when we have a plus b to the power of 3, we have the coefficients 1, 3, which is the coefficient of this entire thing, then 3 again here, and 1. So I have 1, 3, 3, 1. When we have a plus b to the power of 4, we have 1, 4, 6, 4, 1. And likewise, when we have a plus b to the power of 5, we have 1, 5, 10, 10, 5, and 1. So now we'll be using these two triangles to understand the general properties of a binomial expansion. See, what we have obtained here, these are binomial expansions. Why? Because we had a binomial, we applied a particular power to that entire binomial, and we obtained a series of expansions as a result of that power. So these are basically binomial expansions that we are carrying out. So here we are going to now study certain general features of a binomial expansion and how you can carry out a binomial expansion for whatever power you apply to a binomial, maybe a plus b to the power of 24. Uh, so now let's get started. Let's take a look at this first triangle here. From this triangle, we'll first try to see that what's happening to the powers of the individual terms of the binomial. We have a and b, which are part of the original binomial, which will be expanded later on. So now if you take a look, we'll start with the maximum power only, a plus b to the power of 5. So if you take a look here, the first term, alright, even before that, let's take a look at the total number of terms obtained for every expansion. When we have a power of 0, we obtain one term. When we have a power of 1, we obtain two terms. When we have a power of 2, we have three terms. And likewise, when we have a power of 5, we have six terms. This means that if I have a plus b to the power of n, let's say, what is the number of terms that I'll get? Yes, I'll have n plus 1 terms. So the first observation that we can make from this triangle is that the total number of terms, number 1, the total number of terms is equal to n add 1. Now let's come to the second thing, and that is the arrangement of powers of the individual terms of the binomial. So let's take a look at a plus b to the power of 5. The first term has a to the power of 5, and the last term has b to the power of 5. In the first term, you see nothing of the second term of the binomial. There is no b here. And in the last term, you see nothing of the first term of the binomial. Why? Because there is no a here. However, in all the terms that lie between the first and the last term, we have both the first and the second term. Let's take a look at the second term of the sequence. We have something containing a, we have some b here as well. Likewise, we have some a here, we have some b here. So that means that in our expansions, we have, all right, I'll just first correct this. All right, this means that in the middle terms, we have both a and b, but in the extreme terms, the terms at the extreme ends, we have any one of the two terms of the binomial. Now let's take a look at the arrangement of powers. Let's start from the beginning. I have a to the power of 5 in the beginning. You see, there is no b here. But if I say that there is a b here, it won't be wrong. Why? Because here b has a power of 0 and b to the power of 0 is 1. Anything multiplied by 1 remains the same thing. So it doesn't make any difference whether I write b to the power of 0 or not. And similar is the case when I have uh, alright, sorry for the interruption. Let's continue. Right, so we'll now be exploring what happens to the powers. We began with a to the power of 5. In the next term, the power of a decreased by 1. In the term that follows, there is a further decrease in the power of a, followed by a further decrease, followed by a further decrease, and followed by a obtaining a power of 0 in the last term. That means the powers of the first term in the binomial undergo a decrease as we proceed with the expansion. And what's the rate of decrease? One power at a time. So, the second observation from this triangle is that the first term of the binomial has a maximum power in the beginning of the expansion. And what is this maximum power? The power is equal to n. So we are talking about a general expansion, a plus b to the power of n. So this maximum power is equal to n. Full stop. Then in the successive terms, in the successive expansions, it undergoes a decrease by 1 at each step until in the last term it has a power of 0. And the exact opposite happens with the second term of the binomial, that is the b. What happens to b? In the first term, we don't have a b. And I said that, all right, you can say that there is a b, but b has a power of 0. But what happens as we move on? There is an increase in powers. B had a power of 0 in the first term. We had an increase by 1. Then we had an increase by 1 again. And then again. Then again. And then again. So what's happening here is that the second term of the binomial has a power of 0 in the beginning of the expansion. Then, in successive expansions, there is an increase in the power. the power by 1 at each step until in the last term it has the maximum power. And what is the maximum power again? N. That is, when we had a plus b to the power of 5, n was equal to 5. And that is what the maximum power is going to be, both for a and b. Until in the last term, it has the maximum power, which is n. Now, what happens in the terms in the middle? We have seen the increase and decrease, but there's another really interesting thing to notice. Let's take any term in the middle of the expansion. Let's take this one. What is the sum of the powers of a and b? 5. Here again, what is the sum of the powers of a and b? 5. The sum of 5 remains constant throughout the expansions. So the fourth observation from this first triangle is that the sum of the individual powers of the terms of the binomial will always be 5, will always be equal to n. I'm not writing this down here, but this is a really noteworthy thing. Having discussed these three observations, we can now arrange the powers in any binomial expansion. Now remember, there are two parts of a binomial expansion. One thing is arranging the powers, and the second thing is this coefficient, these coefficients. I'm not discussing the coefficients right now. We'll come to the coefficients when we come to the second triangle that I have made. Let's discuss arranging the powers right now. So let's say I have a plus b to the power of 8. A plus b to the power of 8. And how will the expansion go? We'll have in the first term, the first term of the binomial, the first term of the in the first term of the expansion, the first term of the binomial, that is a, would have the maximum power. So we have a to the power of 8. This is followed by a decrease by 1 in the power of a, and b makes its first entrance. So we have a to the power of 7 and b. I have left the space here for the binomial coefficient. In the third term, what will happen is we'll have a binomial coefficient. The power of a undergoes yet another decrease, and the power of b goes through an increase. And similarly, things would continue. A to the power of 5, b cubed. Add a to the power of 4 times b to the power of 4. Add, we'll have our binomial coefficient, a cubed b to the power of 5. Add a squared b to the power of 6. Add a b to the power of 7. Add b to the power of 8. So this is how you are going to arrange the powers in any binomial expansion. I hope this is extremely clear. Now A and B are just some representatives. You can have anything in place of A and B. Let's take the example of maybe 3x plus 2x to the power of 4, and we give this entire binomial a power of 5. So how will we go with the expansions? The first term of the binomial this time is this entire 3x. So the maximum power would be applied to this entire 3x. So it's always safer that while expanding, you make a good use of brackets. So how will I go about it? I'll keep 3x in brackets and give a power of 5 to this entire bracket. Then I'd be having a binomial coefficient. Uh, this entire 3x undergoes a decrease in power. So this is 4. And 2x to the power of 4. makes its entrance. Remember, I kept this whole thing in the brackets. Then again, 3x undergoes a decrease, and 2x to the power of 4 gets a power of 2. Then we have 3x whole squared times 2x to the power of 4 cubed, add 3x, and 2x to the power of 4 has a power of 4, add 2x to the power of 4, this time has a power of 5. This is our last term. In the last term, the second term of the binomial gets the maximum power. Right. So now we are done with the first triangle of the which we made. Now let's come to the second triangle. The second triangle only has the coefficients that we obtained as a result of binomial expansions. Now, since this triangle only contains the coefficients, this triangle and the terms contained in this triangle are called binomial coefficients, and this is a triangle of binomial coefficients. And you know, this triangle has a special name. It's called the Pascal's triangle. So what is Pascal's triangle? Pascal's triangle is basically a triangle of binomial coefficients. Now Pascal's triangle basically tells us this coefficient part of the binomial expansion. We have studied about the arrangement of powers, but we are still left with putting the coefficients in their place. So now if you take a look at this Pascal's triangle, this is a really interesting triangle. There are a lot of interesting patterns associated with this triangle. I won't be discussing any of those patterns right now here, but there's one pattern which is of particular importance to us, and it's just that triangle that I'll discuss, that pattern that I'll discuss. Now, if I know one particular row of the Pascal's triangle, I can work out the second row, the next row using that very row. How is that so? Now, if you take a look at this triangle, the first term of every row is a 1. The last term of every row is also a 1. So here we had n is equal to 0, which gave us 1, n is equal to 1, n is equal to 2, n is equal to 3, 4, and 5. So now when I move on to the sixth term, let's say, so what happens is the first term again would be 1, and the last term would be 1 again. What about the terms in the middle? So let's take a look at the fifth row. How do we obtain the sixth row? Sorry, the first row is just this one. So this is the first row, second, third, fourth, fifth, and sixth. How do I obtain this 5? This 5 is basically a sum of this 1 and 4. How do I obtain this 10 here? This 10 is a sum of this 4 and this 6. How do I obtain this 10? Again, a sum of this 6 and this 4. Then this 5 comes about by the addition of this 4 and this 1. So we can use the same thing to work out the terms of the seventh row. That is when n is equal to 6. So here we would get 6. Here we have 15. Here we have 20. Here we have 15 again, and then we have 6. Likewise, I can work out the eighth row, and the eighth row is when n is equal to 7. The binomial coefficients in that case would be 1, 7, 21, 35, 35, 21, 7, and 1. And in a similar fashion, I can work out what happens when for the ninth row, that is when n is equal to 8. N is equal to 8 is uh, when I apply a power of 8 to a plus b whole to the power of 8. So we have 1, 8, 28, 56, 70, 56, 28, and 8. Now let's go down to the expansion of a plus b whole to the power of 8. I left these gaps here. I can now fill these gaps with the binomial coefficients that I obtained. So the first term has a coefficient of 1. The second has 8. Now if you take a look again at this triangle, you can notice that it is a palindrome. A palindrome is basically a word that is the same when read from either side. For example, the word race car. You read it this way or you read it this way, it's the same thing. Likewise, binomial coefficients are also palindromic. How? If I go this way or I go this way, it's the same thing. So, if I have a 1 as the coefficient here, 1 is the coefficient here as well. If I have 8 here, I'll be having 8 here as well. This is followed by 28 and 28, 56 and 56. Then we had 70 here. So this is how we go about it. And now this expansion is complete. We have the arrangement of powers, we have our binomial coefficients, the binomial expansion is complete. So this tells us basically that if we have this triangle with us, we have the Pascal's triangle with us, we can easily do the expansion. Or even if we don't have the Pascal's triangle, if I want to find the binomial expansion of, let's say, a plus b to the power of 24, and I know the expansion of a plus b to the power of 23, I can use the coefficients obtained in the above sequence, uh, in the above expansion, to find the coefficients for a plus b to the power of 24. But clearly, this method is extremely impractical and long and clumsy. Why? Because obviously it's not always a very feasible option to write down all the coefficients, all the rows of the Pascal's triangle until we reach n is equal to 24. So clearly, there must be a shorter method of going about it. And there must be some pattern that we can use to determine, let's say, the fifth term, the coefficient of the fifth term in the expansion of a plus b to the power of 8. I'll just write down what I said. A plus b to the power of 8. I want a shortcut method to find out what will be the coefficient of the fifth term. The first term, second, third, fourth, and fifth. I need to have a shortcut. Mathematicians now started to look for such a shortcut and such a formula that would help us in obtaining these coefficients directly without the need of making the Pascal's triangle or even knowing the term of the expansion just one step above the expansion that we require, and they were able to come across such a formula. The formula is n exclamation mark upon r exclamation mark times n take away r exclamation mark, and this whole thing is abbreviated as NCR. So now we need to understand this formula. What is n, what is r, and what exactly is an exclamation mark doing in math? So n basically refers to the power that is applied to the entire binomial. So if I have a plus b whole to the power of, let's say, 9, then n is equal to 9. And R refers to the term number. In fact, now here's a catch that's going to come. If you take a look at this uh, row here, this is a row of binomial coefficients obtained when n is equal to 8, right? So what's the total number of terms? The total number of terms is 9. And what happens is that we know that the first term will always have a coefficient of 1. We discussed that and we saw it here as well in this triangle, that when we had a plus b to the power of 5, the first term had a coefficient of 1. So things actually start off from the second term of the sequence, right? So R is the term number starting from the second term. So this would be R is equal to 1, this would be R is equal to 2, this would be R is equal to 3, and this would be R is equal to 8. This is R is equal to 0, right? So if I want to find the fifth term in the expansion of a plus b to the power of 8, what would be R? It would not be 5, it would be 4. Why? Because for the first term, R is equal to 0. For the second term, R is equal to 1. For the third term, R is equal to 2. This means that if I have any term, if I want term number 5, R would be the term number minus 1, right? So R would be 4. If I want to find the fifth term, R would be 4. As a result of this, the term number, alright, I'll come to that when I discuss the general term formula. So n is the power and R is the required term, take away 1. Take away 1. So if I need the fifth term, R would be 4. For a particular expansion, let's say a plus b to the power of 24 again, if I want the 16th term, then R would be 15, and so on. Now what's this exclamation mark? This is the last thing that we'll be discussing in this video, and then we'll be moving on, and then from the next video onwards, we'll be discussing the other stuff. Right. So this exclamation mark basically is called factorial. What's this called? Factorial. I'll write this down here. Factorial. And what is factorial? A factorial basically denotes the product of all the natural numbers starting from that number all the way to 1. So if I have, let's say, 3 factorial means 3 times 2 times 1. What did I say? Factorial basically denotes the product of all the natural numbers alright, let's put it in another way. The factorial of a particular number is a product of all the numbers starting from that number all the way to 1. So 3 factorial is 3 times 2 times 1. Likewise, 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. 7 into 6 into 5, 4, 3, 2, 1. Now I want you to observe something. Alright, now before that observation, I want you to remember this, that factorials go in a descending order, always, never the ascending order. That means 7 factorial will not be 1 times 2 times 3 times all the way till 7, but we'll go downhill. Even though it's the same thing essentially, but this is a convention And why is this convention actually important? Let's see. Let's take 7 factorial. Uh, Now, if I take a look here, I have 7, and then what's this entire thing? This entire thing is actually 6 factorial. So, 7 factorial can alternatively be written as 7 times 6 factorial. And the 6 factorial also can be written as 7 times 6 times 5 factorial. Now this notation is this thing is really helpful in factorial based calculations, and we'll see how. Now before we move on, how can we write n factorial? N factorial is basically n times the number 1 less than n times the number 1 less than n minus 1, and so on until we reach 1. And we can also say n factorial is equal to n times n minus 1 factorial. Likewise. Sorry for the interruption once again. So basically, this mode of writing factorials and working with the factorial notation is really helpful in working with factorials, especially when we are dealing with division in working factorials. How? Let's say that I have to divide maybe 7 factorial by 5 factorial. So I don't need to go all the way up to 5 factorial, up to 1 in either of the cases. Why? Because 7 factorial divided by 5 factorial means 7 factorial upon 5 factorial. And 7 factorial is actually 7 times 6 times 5 factorial upon 5 factorial, and now I can cancel it out. The answer would be 42. Likewise, if I want to find out n factorial divided by n minus 2 factorial, this can be written as n factorial upon n minus 2 factorial, and this becomes n times n minus 1 times n minus 2 whole factorial upon n minus 2 factorial, and all this is cancelled out. We are left with n times n take away 1. Now, why have I discussed this? This is because certain questions of this chapter, binomial theorem, deal with breaking the formula NCR apart. And for that, obviously, you need to know how to deal with factorials. When we come to the past paper questions, we'll see how to deal with them in more detail. I hope this is very clear. If there's any problem, leave your queries in the comments and I'll see what I can do about it. Right. So what have we discussed so far? In this video we discussed firstly how to arrange the powers in a binomial expansion. That is, the first term of the binomial has the maximum power in the first term of the expansion. The second term of the binomial has the maximum power in the end of the expansion. In the middle, there is a change. What happens is that the first term undergoes a decrease by 1 at each step, and the second term of the binomial undergoes an increase by 1 in each step. Now we come to the second step, the second major chunk in binomial expansion, that is the binomial coefficients. The coefficients are obtained using the formula of NCR, where n is the power applied to the entire binomial and r is the required term minus 1. So if I want the eighth term of a particular expansion, r would be 7. If I want the 12th term, r would be 11. We have this button on our calculators, NCR. You'll use the shift button on your calculator. You'll first write n, whatever is n, and then you'll use the shift button, and there's NCR written on one of those buttons. I don't know which button has NCR upon it. You'll press that button and then you will write down R and you will get your binomial coefficient. The rest, we are done with a very major chunk of this chapter in this very video. In the next video, we'll start from here. We'll discuss something called the general term formula. We'll do some expansion, some binomial expansions using the NCR notation, and let's see. Hopefully, we'll try to complete this entire chapter in the next video. Till then, Assalamu alaikum wa rahmatullahi wa barakatuh.